Next, let's look at the paging allocation mechanism. As we have mentioned in the previous slide, the major feature of using paging allocation mechanism is that process physical address space can be non-contiguous. As long as the total size of a free physical memory space is large enough to hold the process, and the process can be allocated on that physical memory space. Therefore, paging mechanism can totally avoid external fragmentation problem, and also avoid the problem of a different size of memory chunks. The main idea is quite simple, so we just divide the physical memory into fixed size blocks, which we call it frames. The size of a frame is based on the power of 2. So commonly the size of a frame is from 512 bytes to as large as 16 megabytes. And also, we divide the logical memory into blocks of the same size of a frame, so which we call it pages. So when we refer frames, we are talking about the physical memory. On the other hand, so when we mention the pages, actually we are talking about the logical memory. In paging allocation mechanism, we need to track all the free frames. To run a program of size n pages, so we need to find n free frames on the main memory, and then we can load the program into those n free frames. Since n free frames may not be contiguous and in order, so we need to set up a page table to help us translate the logical addresses to physical addresses. And also, since the swapping mechanism is supported by the system, so that the processes can be swapped out and in between main memory and the backing store. So therefore, the backing store also needs to be split into pages. Although the paging mechanism can avoid the external fragmentation problem, but the internal fragmentation problem is still remaining due to the fixed size of memory blocks. Next, let's see how to implement the address translation from logical addresses generated by the CPU to the non-contiguous and scattered physical addresses. So basically, the logical memory address generated by the CPU is divided into two parts. One part is called page number, which is denoted by P. It is used as an index in the page table, which contains base address of each page in physical memory. Another part is called page offset, denoted by D, which is combined with a base address to define the physical memory address that is sent to the memory unit. The following figure shows the rough idea. For a given logical address space 2 to the power of m, and the page size 2 to the power of n, so we have a logical address with m bits to denote the total size of the process. And also, since the page size is 2 to the power of n, so we can use lower n bits of m bits to represent the page offset. Then the total number of pages for the corresponding process will be m minus n bits. So if you cannot get the point right now, so don't worry, we have a couple of examples to help you understand it in the later slides. In order to efficiently translate the logical address into a physical address in paging allocation mechanism, the paging hardware can help us do a very efficient. The following figure shows us how to do it with a paging hardware. So when the CPU gives a logical address, according to the page number P, the paging hardware can find the corresponding frame to that page number P on the page table. And also because the page and the frame have the same size, so both logical address and the physical address can share the same page offset. Then we just combine the frame with a page offset. We can allocate the data or instructions on the physical memory based on the logical address. Then let's see the paging model of logical and physical memory. On the left side of this figure, so we have the contiguous logical memory pages for a newly coming process. In this example, it has 4 pages from page 0 to page 3. And on the right side, it shows us the physical memory space, which has 8 frames from number 0 to 7. And in the middle, we have the page table, which maps the contiguous pages to physical memory frames, so that we can allocate the logical memory space into the physical memory space. So here we can see the page 0 is mapped to frame 1, 1 to 4, 2 to 3, and 3 to 7. And on the physical memory shown on the right side, we can see that the pages are allocated on the scattered frames and out of orders. Then let's look at a more specific paging example in this slide. In this example, we assume the total physical memory size is 32 bytes, and the page size is 4 bytes. Then we can calculate the page offset n is 2. We assume the total logical memory space m is 4-bit. Therefore, the total number of pages is 2 to the power of m minus n, which is equals to 2 to the power of 4 minus 2, and then equals to 2 to the power of 2 equals to 4. So we have 4 pages in this logical memory space. For the total number of frames can be calculated by 32 divided by 4, which is equal to 8. So we have 8 frames from number 0 to 7. When we locate the frame number to the physical memory address, we can use the frame number times the page size 4 to get the correct physical address. For example, the physical address for frame 5 is equals to 5 times 4, which is equals to 20. And the frame 6 is equals to 6 times 4 equals to 24, and so on. For the page offset, it is exactly the same in both logical page and the physical frame.